back to eCoreAcademy students. My name is Anita and I am one of the teachers and co-founders here. As you can see, I'm bringing you a new Algebra 2 lesson today. It's going to be a continuation of the quadratics unit we've been doing in Algebra 2 so far. The last lessons have been called Modeling with Quadratic Functions. If you haven't seen them, I highly suggest to visit our channel and watch those before watching these because they complement one another by going in a sequential order. As you can see, this is quadratic applications. So everything we've been doing with modeling with quadratic functions is really building up to this. So we're seeing what real-life scenarios quadratics can be used in because I know a lot of these algebraic concepts can be so far-fetched and otherworldly to a lot of us. In this part of this chapter, we're going to be looking at specific cases where quadratics can be used in real life scenarios. This is going to be part one where I introduce you. So now that the preparation is done, as in we understand how to model real life scenarios with quadratics from our previous few lessons, let's get into some scenarios where you will see word problems of quadratics. So this first lesson is really meant to just break down what the zeros of a function are because those are going to be very important in word problems. So I really want to go over that. That's going to be the first part of this lesson. Then we will be going over different scenarios in which you will be seeing quadratic functions. So I'll give you some examples of ones that I've seen. I've gone through all my notes and collected examples, scenarios. I'll explain them to you. So if you take an assessment, nothing seems too far-fetched for you. And then lastly, we'll be doing one word problem together using the TI calculator. Next, the lesson will be more dedicated to looking at these different scenarios and tackling each one because at their fundamentals, they're all about quadratic applications and asking about different parts of a quadratic function. It's just all this mathematical stuff is masked behind these everyday words you see, everyday scenarios you see. So we're going to be dissecting it and understanding quadratic applications. Okay, so before I even get into the lesson, I would really appreciate it if you paused and liked the video to support myself and AJ as teachers here at eCoreAcademy. Also, subscribe to the channel so you can join our expanding student community you don't want to miss out. Please hit the post notification bell so you're notified of our latest posts. And don't feel afraid to drop a comment down below. We love to start conversations and hear what our students have to say. Lastly, use the socials in the description box below to share eCoreAcademy with family and friends who could benefit from it as well. By sharing, you are doing goodwill for the community and you are helping other students who could use this learning tool to enhance themselves academically, especially during this situation the pandemic has put us in. Okay, let's go to the next slide. Here, let's talk about zeros of a function. This is what I was just mentioning. So zeros of a function. We can graph any function on the TI calculator and see where it crosses the x-axis. This is where the function equals 0, and so the process is called finding the zeros of a function. This is important to quadratic applications because they tell you the starting value. So let me just explain everything that's up on the screen right now. We can graph any function on the TI calculator. Remember, TI calculator is your Texas Instrument calculator, or you can graph it by hand. It really doesn't matter. I'm just using the TI calculator in this situation because with most word problems, we're going to be using the calculator because it's just faster to solve them, and we can see where it crosses the x-axis. So for those of you who don't remember what the x-axis is, let me just draw a coordinate grid real quick here. This is just a rough coordinate grid, but this right here, this vertical line would be your y-axis, and then this horizontal line would be your x-axis. So we can graph any function, any quadratic in this case, any function really on the TI calculator, and then we can see where it crosses the x-axis. So what does this mean? So if we had this quadratic function, you can see this is clearly a parabola. Well, it crosses the x-axis at these points that I am drawing like big circles at. So that's what it means. So where does it touch the x-axis? We can see that on the TI calculator. This is where the function equals 0. If you see the second bullet, this is where the function equals 0. So what is the function? So let's just look at a linear function, for example. See how it's y equals mx plus b. So whatever your y value is the value of the function at a given point. So if I had a given function, a random function, and if I gave you the point 2, 1 and said that the point 2, 1 lies on this function, Well, the value of that function at the point 2, at that point is 1, because your y value, your y coordinate, is the value of a function at a given point. So this is where the function equals 0. Therefore, this is where your y equals 0. You're probably familiar with the fact, with us talking about how we make x equal to 0, and we find where the y-intercept of a function is. Well, this is the total opposite. We're finding the x-intercept. That's what a 0 of a function is. It is your x-intercept. So it is where your y is equal to 0. Therefore, you're going to be passing through the x-axis because you're going to be given a point x, and then your y-coordinate will automatically be 0. So that's what it means by this function is equal to 0. So your x value is, your y value is going to be 0 in this case. And so the process is called finding the zeros of a function. So that's just what we call this process. When you hear finding the zeros of a function, zeros can also be called x-intercepts, can also be called solutions. We'll be talking about that when we get into factoring quadratic functions. So they have many names, but just know it's when your y equals 0. So that is what it means when we're finding zeros of a function. It's important in quadratic applications because they tell you the starting value. So what does this mean? Let me reference a linear equation. Maybe it'll be easier for you to understand. So if we have the value b in this linear equation I've written on the screen, y equals mx plus b, oftentimes when we do word problems with linear equations, we see b as the starting value. So let's say I am putting money in a bank, and my savings are increasing at a linear rate. This is not usually the case, but let's say I put money in the bank. Let's say I put $100 in the bank, and every month I'm getting, or let's just say that I put $100 in the bank and it's increasing at a linear rate. Well, my starting value is 100, and that's really important to know because you need to know where this is starting so you know how this function is going to develop and grow or decrease over time. So that's why it's important in quadratic applications, because they tell you the starting value. Oftentimes, you'll see quadratic functions where your x-intercepts, your zeros are your solutions. That's where this starts. So you might have a scenario where someone is throwing a ball into the air, and the x-intercept, your 0, is a question. They'll give you a quadratic function in the form of standard form or vertex form in the problem, and they'll ask you a question. Where did the ball start? Like where was the ball first thrown? And your x-intercepts and your zeros will help you answer those questions. So just know that they're very important in quadratic applications because they tell you the starting value. So let's go to the next slide. We've come to the next slide where I'm showing you a zeros example. So what does this exactly mean? Based off the information I showed you from the last slide, we're actually going to be doing a problem so you understand how do you find a 0 on a calculator. This is not going to be a scenario like you see in a word problem. Like I said, it's going to be masked by words. So you need to pull from those words what it's asking you to find. It might tell you one thing in like our common day language, but then it's actually asking you what are the zeros of this function. The zeros are the answer. So in order to actually find those zeros, you need to know how to use your calculator. If you're doing it by hand, of course, doing it by hand as well. So here's the problem. Solve the following by graphing on the TI calculator, then give the answers to the nearest thousandth. What I've given you is x squared minus 8x plus 6 equals 0. And what this pretty much means is you can see that x squared minus 8x plus 6 is in standard form. It is a quadratic. So I wrote beneath these two. I already wrote these out, but you can break this down into y equals x squared minus 8x plus 6, and then the second would be y equals 0. And by doing substitution method, you can see that both of these equations would be equal to one another. Hence, x squared minus 8x plus 6 equals 0. So that's where you get that from. That's how you break this down so you can represent it in a more common like a function. So these are the two equations that we've broken this down into. So how do we solve the following by graphing on the TI calculator? Well, what you're going to do is you're going to graph x squared minus 8x plus 6. You're going to put it in your y1. You're going to get your parabola. You should be familiar with that. Then in your y2, you're going to put 0. And what we're trying to do is we're trying to find where your y equals 0 intersects with x squared minus 8x plus 6. You might be wondering why is y equals 0 important? Well, first of all, it's a horizontal line. It has no slope. As you can see, there's no x here. So it's a horizontal line. Also, y equals 0, if you think about it, it's the x-axis. Just how x equals 0 is the y-axis, y equals 0 is actually the x-axis. So by graphing a line that represents the x-axis, and then graphing our parabola of our quadratic that represents our quadratic function, by finding the points where these intersect, maybe it's 1 point, maybe it's 2 points, maybe it's no points at all, we find the x-intercepts, which is exactly what we're looking for. So that's the method that you would use to find the zeros when you're given a word problem. So as you can see, I've already written this 2 solutions. There are 2 of them, 2 places where your parabola will cross the x-axis, and in these cases x equals 0.838, and the second was x equals 7.162. Again, I rounded to the nearest thousandth. Now let me show you actually how to do this on the calculator, so you can do this for all the word problems to come when you're asked to find the x-intercepts, or intercept, or no x-intercepts at all. So let me pull up my calculator. I suggest you get yours out too and follow along. Okay, grab my calculator. I already cleared it, so I highly suggest you do that, just so you start from scratch, clean, and you don't get confused by any other values you put in your calculator. Just start fresh. And to do that, you would hit second mem 712. You should be familiar with that by now. Go ahead and do that. I'll give you a second to do that if you're following along with your own calculator. Okay, so now let's solve the problem. Like I said, first we want to go to our y equals. So in our y equals, you can see it's all empty. Also, I forgot to mention, on the right-hand side, you see this panel where all of the buttons I press will be mentioned. So if you don't have a calculator, or you're just following along and you're going to be using a calculator later, you can follow along and see what buttons I'm pressing, especially if you can't see the screen very well. So that just pay attention to this and you'll know exactly what I'm doing. So in our y1, we want to enter this first equation in red. I've written a y equals x squared minus 8x plus 6. So that's what we're going to be entering first. So y1 is x squared minus 8x plus 6. So that is our y1. In our y2, we want to enter that y equals 0. So I'm just going to type 0 and we're done. That's just going to represent the x-axis. So it's easier for us to find the intersection because now we've actually made it a line. So it's going to be, the calculator is now able to find the points where it intersects. And in order to see these two, let's hit graph just so we can see them. Make sure we can see them. Make sure we don't have to adjust our viewing window or anything. We can see our parabola, and we can also see that y equals 0 line, and it falls right on top of the x-axis. Again, it's a representative of the x-axis. As you can see, this parabola intersects this the x-axis at 2 points. This point over here to the left is one of them, and this point over here to the right is one of them. Because they're both x-intercepts, you need to find both of them. That's why in the solution I gave you 2 values. There are 2 intercepts in this problem. You need to find both of them. So how would we do that? We do our regular find the intercept of a between 2 lines method that we've been using. If you don't remember, let's go over it right now. So we're going to hit second, and then we're going to hit trace to go to the calc menu. Hit 5 for intersect. Hit 5. You'll be brought back here. As you can see, the cursor is closer to this intercept over here to the left. So what we're going to do is we're going to hit enter 3 times. We're going to find this left intercept first. And then after that, we have to purposefully move the cursor to the right side of the parabola so we can also find this right intercept. You don't want to exclude this one. First, let's find this one. Hit enter 3 times. 1, 2, and then 3. And then you get the same answer I got down here, 0.838 rounded off to the nearest thousandth. So we found the first one. Let's find the second one. You want to repeat that same process over again. Second, trace, and then 5 for intersect. And then you see how the cursor is blinking very close to this left intercept? Well, we've already found it. We're trying to find the one on the right. So use your right arrow and purposely just move that cursor over to the right-hand side of your parabola until it's pretty close to your right-hand intercept, the one that you're trying to find. Now you're going to hit enter 3 times. 1, 2, 3. And you should get that second answer I got down here, 7.162. 2. You can just round to the nearest thousandth. So that is how we found the two intercepts. You might have 1, 2, or none, like I said before. Just look at the graph, make sure you can see the entire graph, and then go about it that way. Make sure you include all intercepts if you have multiple. So those are my pointers. Now let's get into the actual word problem. Before we even get into the word problem, my mistake, I have a very, very important slide right here called application scenarios. So here are some scenarios, you might see with quadratic applications. So I went through my whole notes packet I've gotten from Algebra 2. I went through all the word problems, and I picked out different scenarios that I saw recurring or really stood out. So everything my teacher gave quite a bit of practice problems. So this is going to cover most of what you're going to see with quadratic applications. If you're the type of person who's like, let me prepare myself for the scenario I'm going to see, let me know what I can possibly expect. So here are some scenarios. First one is people jumping. This could be over a fence, over an object, just jumping in general, jumping over a jump rope, just people jumping. Because with all these scenarios I'm going to explain, think of that parabolic shape. So if a person's jumping, they do form a parabola when they jump. So imagine each of these scenarios I'm mentioning and think of the parabola that is formed when an object is in motion or anything like that. It's not always going to be a parabola. There's other scenarios where you have quadratics, like area, where you have squared. If you think about it, if you think about area, it's a squared term. We talk about square feet, square inches, whatever unit of measure you use. It's always going to be referring to that quadratic, that base. Second one is throwing or dropping objects. So the next problem is going to be about a child throwing a rock. It can be people throwing balls, people just throwing objects or dropping them. So someone we talked about this in the last video actually. Like AJ in that word problem scenario stood at the top of the building and threw a ball off the building. So throwing or dropping objects, they form parabolas. By throwing, I'm talking about throwing an object straight up, a little bit forward, but mostly upward, to form that parabola. Next, you have rockets and probes. So when you send a rocket or a probe into the atmosphere, it's kind of formed that parabolic shape because oftentimes they do circle around the Earth, but you're sending it into the atmosphere and then it's going to gradually come back down to Earth. So you're going to see problems with rockets and probes, especially like toy rockets or rockets you under in science fairs being launched into the air and then they drop down where you're just competing for height. So those kinds of things. Next, you'll see number sense. I'll be talking about this later. So you're going to be given some clues about some numbers and you're going to have to form your own equations using those clues, and you have to find what the actual numbers that are being referred to in the problem are. So by number sense, you're trying to find numbers, kind of like a puzzle kind of trick, but it's a word problem that you will see on an assessment. Next, you have ranchers and gardens. These used to be one of my most difficult problems for me when I took an assessment, but you're going to be talking about farms, gardens, pens, fences that ranchers or farmers use to keep cattle or any kind of livestock or even gardens in. And they're going to be asking you questions about here's the amount of space I have. Please develop a quadratic function to represent what the length should be, what the width should be, where should I put the divider between my pastures, things like that. The next one is production rate. So like manufacturing, you'll be given the manufacturing rate of a factory. They'll talk about how much they manufacture a day, how much actually goes to market, how much is faulty, things like that be represented by a quadratic function. Next, you have baseballs and other balls. What this just means is just like throwing a ball, hitting a ball. If you play cricket or baseball, when you hit the ball, if you hit it pretty high, it can form a parabolic shape. Any balls, if you're kicking a soccer ball, if you kick a pretty high ball, if your goalie punts a ball, it forms a parabola. So that's what I'm talking about there. Rugs and interior design, I just mentioned that. Area is a squared term, hence quadratics are also squared terms, so you'll also see those go hand in hand. You might be asked a question where, you have this much space in a room, so what can the dimensions of the rug be? And obviously it's going to be a more difficult problem, more difficultly worded, but that's pretty much what it means. Next, you'll have tables like an actual table that I've shown you, and you're going to be asked scenarios. I remember showing you all a table about here are the recorded temperatures over the course of a day in Voorhees, New Jersey. And you had to graph a quadratic model and find the quadratic regression through it. That's the kind of table I mean. So you'll see realistic scenarios like that. Then you have diving. What do I mean by diving? Well, people diving off of bridges into water, people diving into water anywhere. Also, you'll see birds that dive because often you have birds of prey diving to catch their prey, and you'll be talking about diving in that case. Then you have hot air balloons. When hot air balloons take off, yeah, they take off at a more like slanted pace, but then when they come back down pretty soon. If you've ever been in a hot air balloon, just for leisure, they'll come back down soon, and it's actually like a parabolic shape. So hot air balloons, you'll also be seeing those. Shooting and arrows. So if you're at like, I know not many people do this, but if you're at a gun range, a place where you shoot guns, or if you use bow and arrow, whatever you use, especially if you're shooting something like a bird, something that flies, well, you're shooting an arrow or a bullet like toward, if this is the bird right here, you're shooting the arrow or the bullet towards the bird, and then the bird is going to actually fall down after you hit it and kill it. So the whole range of your arrow or your bullet, it goes upwards from where you shot it, hits the bird or predator, prey, whatever it is, and then your prey is going to fall downwards. So if you saw that, it was like a parabola. So that's what I mean by that. Bridges, well, bridges look like parabolas. I remember talking about this when I mentioned real world scenarios. Bridges are parabolas. So you're going to have questions about building bridges or dimensions of bridges, and those will be related to quadratics. And lastly, packaging boxes. So like dimensions of boxes, like what is the best way? There's a company that's asking you what is the best way to maximize the volume we have in the box so we can have the most amount of stuff in this box with these given dimensions and so forth. So just the relationship between length, height, and width. And it comes with packaging boxes, and you'll see how that applies to quadratics. So if you want to just pause the video and just look over all these scenarios I gave you, I highly suggest it. We're not going to be going through all of these scenarios because I'm not going to be making lessons on every single one of them. I'll pick out the most like difficult problems that I struggled with and what my classmates struggle with from what I've heard, and those are what we're going to be going through. The rest of these are pretty straightforward, especially the ones where you have scenarios where there's a parabola being formed, like people jumping, objects being thrown, rockets, baseballs and other balls, diving. Those kinds of things are pretty straightforward because something is being thrown or jumping or diving or whatever. It's following a parabolic shape. However, there are other problems like number sense and ranchers and gardens and production rates and packaging boxes that don't necessarily apply to parabolas but apply to quadratics. So that's what we're going to be that's what we're mainly going to be focusing on. However, for the sake of this video, we go to the next slide. We're going to be looking at a problem on throwing rocks, so you get an idea of what those parabola-based quadratics are about. So I'm going to give you some information, and then on the next slide, I'm going to be asking you a series of questions that we're going to be solving using the calculator. So here's the throwing rocks thing. I know I would highly discourage children from throwing rocks, but it's just the problem, so let's read it together. A child throws a rock into the air. So imagine a child, I don't know, in your front yard, on the sidewalk, somewhere where he or she is not going to hit anybody, but throwing a rock. A child throws a rock into the air. So this child is throwing it upward into the air, not straight forward, not straight at the ground, upward into the air. The path of the rock resembles a parabola, like I said, with an equation of y equals negative 1/8 t squared plus 3t plus 4, where t is the time in seconds from the moment the rock left the child's hand. So the t in this, you could also see it as your x. Your t is the amount of time, your independent variable, your x coordinate. So it is, as soon as that rock left the child's hand, someone started the clock, and t is recording how many seconds it's been since the child threw the rock, and y is the height of the rock in feet. So at one given time, which is your x coordinate, the rock is y feet up in the air. So that's the relationship between the two x. Let me actually write this down here. T, which is your x, represents time in seconds, and you should probably know this by now, but I'm just gonna write it anyway. And then y is your height of the rock at a given time, and it's going to be given in feet. So just know that that is the unit we're going to be using in this problem, feet. So those are the two variables you need to focus on. That's the information we've been given. So now let's get into actually solving this problem. I've switched to a view of my calculator so that you can better view it on the physical calculator as opposed to the electronic calculator. I'd really appreciate it if you gave me some feedback and let me know which you prefer, the electronic one or the physical one, whichever one's easier for you to follow along with me on, see like the actual computation I'm doing, etc. So just let me know in the comments down below. Meanwhile, let's finish solving this problem. For your convenience, I've written the problem at the top of the screen, which is just the quadratic function that represents the path of the rock as it leaves the child's hand. It was my mistake because I had written on the previous slide y equals negative 1/8 t squared plus 3t plus 4, but the actual problem is plus 2t. So that's my bad. I really apologize for that. It's plus 2t. So that b term is 2, not 3. So the actual quadratic function should be y equals negative 1/8 t squared plus 2t plus 4. So make sure that you get that down right. My apologies. I messed that up on the last slide. Okay, so now let's solve these 6 problems I have. They're going to appear to the left on the chalkboard. You'll see them when I click the next arrow. So the first question I have is, what is the maximum height of the rock? So in this case, since the child is throwing the rock up into the air, you can imagine the parabola that the rock forms as it goes through the air. Well, that parabola, its vertex is the maximum. So that's going to be the highest point of the rock. That's going to be the highest point the rock hits before it starts descending towards the ground. So in order to find that, let's go to our calculator on the webcam. If you look over here, if you have a calculator, please follow along with this. It would be helpful and beneficial for you as you walk through this problem with me. Before you start, I recommend that you clear your calculator. To do that, hit second, mem 712, and you should be familiar with this. You'll get this RAM cleared screen. You're good to go. So first we want to actually put this equation that we have into our y equals. So hit your y equals, and you'll be taken to your y equals screen. In your y1, you want to type this equation we have up on the screen. So negative 1/8. And remember, your t, which is your time in seconds, is actually can be substituted as x. So it's understood that t is x. Remember, your y is your height in feet given at a specific time. So instead of writing t, I'm going to write x. So x squared plus 2x plus 4. So now I have this in my y1. Let's just hit graph to confirm if we can see the whole graph. And it's graphing. Well, the only problem here is that we can't see the vertex. We only see like the left side of our parabola. So in order to see the whole thing, we're going to go to window and adjust our viewing window. So if you scroll down to your x max, I'm just going to change that 10 to a 20 for good measure. Go down to your y max, and we can change that 10 to a 30 just so that we can make sure that we can see that parabola. And as you can see, graphed, you can see both of the x-intercepts and the vertex, so I think you're good to go. That would be my rule of thumb for you if you're trying to make sure that you can see the whole most of the parabola. So to find the maximum, which is the vertex, which is right up here, you want to hit second and then the trace button, and you'll be brought to the calc menu. You want to hit 4, which brings you to maximum. And then you'll get this left bound question. Remember, the calculator is asking you to guess a point to the left of the vertex, a point to the right of the vertex, and then finally the vertex. This point is to the left of the vertex. I'm just going to hit enter to confirm that. Then I'm going to hit the right arrow, and I'm just going to scroll to a point that is to the right of the vertex that is pretty symmetrical to this point on the left hand side, and you can see my cursor is about the same distance from the vertex as that first point I plotted. Hit enter again, and then your last enter is going to be your guess, so you're going to guess where the vertex is. You pick a point right between those two vertical lines you just graphed and hit enter one last time. And then you will be given this maximum. Your x is 7.9999999, and y equals 12. Remember, your calculator is not going to be perfectly accurate. If it's giving you something like 7.99999, it's most likely you most likely have to round to the number up. So the correct answer for your x coordinate is probably 8. So that's just a rule that I would remember if I were you, especially if you're doing assessments or a lot of problems like this. Remember, just if you get an answer like 7.99999, it's most likely the number up. So in this case, it's 7.999. So it's probably 8. X is probably 8. Y we got a clean integer. Y equals 12. So if we're asked what is the maximum height of the rock, well, X is responsible for your time in seconds, Y is your height in feet. So the answer to this question would be our Y coordinate. So if Y equals 12, then the maximum height of the rock is 12 feet. If I hit the next arrow, you'll see that on the left it appears in a blue highlight. 12 feet is your answer to that question. The next question is, when is the rock at its maximum height? So the key part of this question is the word when. When indicates time. And your X variable, which is your dependent variable, is responsible for time. In this case, you can see the maximum, which is the highest the rock will be. We already see that the highest the rock will be is y equals 12. This question is asking us when the rock is at 12 feet, what is the time? And to find out what that is, you just go over to your x-coordinate, and your x-coordinate is 7.999. Again, you'd round that up to 8. So to answer this question, when is the rock at its maximum height, you would say 8 seconds. If I hit that next arrow, you'll see 8 seconds. Okay, let's go to the third question. What is the initial height of the rock when it leaves the child's hand? So what are we being asked here? So what is the initial height of the rock when it leaves the child's hand? So we're pretty much being asked, what is the height of the child? So what we're pretty much, like I said, we're being asked, what is the initial height? Well, if you imagine the child standing there, you can clearly see that imagine that the child is holding the rock. So whatever the child's height is, that is going to be when the rock leaves the child's hand, because the rock is starting with the child. It's going to be your starting point. So if you look at this graph right here, we actually don't need to do any computation using this calculator. We can easily derive this answer from the quadratic equation we've been given that's at the top of the screen. If you're wondering, Anita, how do you do that? Well, just listen and I'll tell you exactly how. You can see that this parabola intersects the y-axis. So the y-axis in this case is responsible for your height. So you can imagine that the child is standing right here where my index finger is, and he or she is throwing the rock into the air, and it's going to fall right here where the parabola touches the x-axis. Imagine the x-axis as the ground the child is standing on, and the y-axis as the height. So if the rock is being launched from here, this point, whatever it is, you can clearly see it's not at 0, 0, the origin. It's a little bit above that. This indicates that the rock is being launched at the child's height. It is being launched at the y-intercept of this quadratic function. So when t is equal to 0, when time is equal to 0, before the rock has even been launched, that is what we're trying to find. We're trying to find when t is equal to 0. That will indicate what the child's height is, and the child's height is the answer. That is the initial height of the rock. So as you can see, if you look at y equals negative 1/8 t squared plus t plus 4, your negative 1/8 is your a value. Remember, this is in standard form. 2 is your b value, and 4 is your c value. C value is important because it is your y-intercept. Therefore, the answer to this, what is the initial height of the rock when it leaves the child's hand? It would be 4 feet, because 4 is your y-intercept. 4 is where this quadratic function touches the y-axis when your time in seconds is equal to 0. It's the starting point. So that is how you would have solved that, just by looking at this function that we've graphed on the calculator. Okay, let's go to the next slide where I have a series of more questions, just 3 more. Okay, so we're just going to continue on. Again, the problems at the top of the screen for your convenience. When is the first time the rock will reach 6 feet? So the question is asking us for the time. So the time we are given a y value, which is 6 feet. We're going to be asked for the time. So we've been given a y value. We're trying to make a prediction for t or for x. In this case, if you remember, we would graph this 6 feet as a separate line. So in our y2, we would put 6 in. We would get a horizontal line. It has 0 slope. We would find the point where it intersects this parabola the first time. So let's do that right now. I'll show you exactly how. Go to your y equals and go to y2 and type 6 in, because we're asked when's the first time the rock will reach 6 feet. And if you graph, you'll see that this red line representing your y equals 6 is graphed right through it, and it intersects the parabola at 2 points, 1 point over here and 1 point over here. And what we're being asked is, when will the rock reach 6 feet for the first time? So this is the second time it will reach 6 feet. This is the first time. This is what we are trying to find. In order to find this point, we're going to find the intersection between the parabola and this horizontal line. So hit second and hit trace to go to your calc menu. Hit 5 for intersect, and then you will see your cursor. As long as your cursor is closer to the point you're trying to find, which is this point over here, we're good to go. If it's closer to this point, then it's going to find the value of this what the coordinate pair for this intersection is. We don't want that. So as long as it's closer to this coordinate pair of the intersection over here, you're good. So you want to hit enter 3 times. 1, 2, 3, and you are given this point right over here. So if I hit the next arrow, you will see the answer. Remember, we're asked for t, which is time, which is your x coordinate. We already know y is the feet, so we're asked for time. So your answer would be your x coordinate. I rounded off to the nearest thousandth. It would be at 1.072 seconds. So that was how you solve that. Let's go to the next question. Will it ever reach 6 feet again? If so, why and when? So first, let's answer the question, let me just hit the next arrow so you see the answer. Will it ever reach 6 feet again? Well, we already answered that question. If you look at this parabola right here, over here, the parabola hits that y equals 6 horizontal line again, which indicates that there is a second time that the rock hits 6 feet, and that is after it starts descending back towards the ground. So the answer is yes. If so, why and when? So let's answer the first question, why. The rock will fall back down and reach 6 feet again in its decline. So after it hits that peak, the rock has to come back down. And we've already said that the maximum height of the rock is 12 feet. So if it has to come from 12 feet up in the air back to the ground, which is 0 feet, it's going to pass 6 feet. Therefore, the rock will fall back down to 6 feet in its descent. Now we've got to find what the time in seconds is when it reaches 6 feet again. I know the answer is already up on the screen, but let me show you how you would actually do it on the calculator. Again, you want to hit second and then trace. You're brought to this calc menu. You want to hit 5 for intersect, which is exactly what we did over here. But remember, you want to purposefully hit the right arrow and scroll over to that second point, because you want to make sure your calculator picks up on this point, not this point. As long as your cursor is blinking closer to this second intersection, you're good to go. Mine is obviously closer to this one, so I'm good to go. I'm going to hit enter 3 times. 1, 2, 3. And then you are given the second point. So after hitting enter 3 times, I got the answer here on my calculator, 14.928. On the screen it says 14.242. If you're in that range, I'd say you're fine. My calculator is being a little bit wacky, but just make sure you're in that range. If you get one of those two answers, you're probably good. You want to try it a few times and make sure that you are doing it correctly on your calculator, and you are fine. Let's go to the next and final problem. When will the rock land on the ground? So what is this asking us? So it's asking us for an x-intercept. How can you tell? Well, it's asking us when the rock will reach the ground again. The ground is your x-axis. So it's asking when will the rock hit the ground. Therefore, in order to find where it intercepts the x-axis, we're trying to find this point right over here. The child launched the rock, and now we're trying to find where it lands over here. So in order to do that, you want to go to your y equals, go to your y2, and clear this 6 out and put 0, because remember, y equals 0 is your x-axis. Hit graph, you'll get your parabola again, and then you will get your horizontal line graphed through the parabola. Next, you want to find the intersection over here. To do that, you'd hit second, trace, and then you would hit 5 for intersect. And I would just hit the right arrow so I get closer to, I want to get this intersection point to the right, not this one to the left. So I'd scroll over to the right. I hit enter 3 times. 1, 2, 3. And then if I hit the next arrow, you see the answer is 17.798 seconds. So that is when the rock will land on the ground. Remember, the key question is when. We already know y is going to equal 0 because 0 feet is the ground. We're asked for a when, which is the time, which is your x-coordinate, and we would give that in seconds. So I'd look at your x-coordinate, round that off to the nearest thousandth, and then you'd put that down as the answer. So that is how we would solve these 6 problems that all go along with that information we just read. So I hope you found that helpful. Well, I hope you enjoyed that video. I'm sorry for some of those some of those errors with the numbers, but hopefully you got the idea. We're going to be doing a part 2 where I'll run you through 2 more quadratics, 2 of the harder kinds of problems that I found. The 2 of the problems that I found were a little bit harder, so hopefully that will be helpful as well. For now, I would really appreciate it if you hit the like button to support myself and AJ as teachers here at eCoreAcademy. Also hit the subscribe button so you can join our expanding student community, and don't forget to follow us using our socials, Facebook, Twitter, and Instagram. We have all 3. You can find them in the description box below. We also have a website coming up soon. I know I keep saying this, but I really want to reiterate it. It'll be so useful for all of you students with all its sweet functionalities. You'll get access to all these videos, and in addition to them, you'll be getting access to notes, exclusive notes from AJ and myself on all these topics that we've taken in class. Guys, we've been through these courses, we've got the notes, and we can help you be successful in these courses as well. Just remember to access the website. And finally, we'll have a self-evaluation quiz for all of you so that you can get used to some of the kinds of problems you'll be seeing regarding these topics. Lastly, we have a Gmail, so if you have any personal or business correspondences that you'd rather not put in a comment under our YouTube videos, please feel free to email us at eCoreAcademy@gmail.com. This can also be found in the description box. Well, that's all I have for you all today. I hope you enjoyed the video, and please look for Quadratic Applications Part 2. Have a great day. Bye!